We are going to see about Lamport's distributed mutual exclusion algorithm. Mutual exclusion means that is, it's actually a scenario where only one process can use the shared resource. The problem when happens means actually the same resource will be accessed by more number of process at a particular moment, then there is a problem. Okay, so mutual exclusion means at a particular time only one process can access the shareable resource. Once its task is over, then the next process can use the same resource. That is the meaning of mutual exclusion. So now we are going to see about how to achieve this mutual exclusion in a distributed environment. Okay, so as we all studied that in the distributed environment there are a lot of a node or how we can say different sites, right? That is, every site we have a different process, or they are, and all the sites are geographically separated at different locations. So at this situation we are going to have this type of we are going to ensure when more number of sites going to access the same resource, how we are going to manage in a distributed system. That is the problem. Okay, so Lamport's algorithm is one algorithm that helps to solve this mutual exclusion problem in a distributed environment. So now we can see the what is that Lamport's algorithm. It's very simple algorithm. So this algorithm is basically a category of non-token based algorithm. Non-token based algorithm in the sense, I already explained this meaning in the class also. Actually, non-token based algorithm means that is we are passing some messages. That is all the process involved in this distributed networks, who are all the process involved in the communication. All the process going to send some messages among them to confirm who is going to enter the critical section. Okay, so critical section is the region where the shared resources available, right? So at a particular time, only one process can enter into the critical section and access the resource available in the critical section. So here this non-token based algorithm fully based on passing of messages, send or receive, like the same kinds of messages only pass between the processes or between the sites. And one more thing is there, this Lamport algorithm stress that every process maintains one timestamp. Every process maintains a timestamp in the message. So whenever it transmits a message, it has two field in the each message. Okay, so one message is called as a timestamp and the another part is called as the process identifier. So timestamp and process identifier are the two major fields of the request messages. Okay, I will send you the next slides. So timestamp also plays an important role in the Lamport's mutual exclusion algorithm. For example, just we are going to see an example. Imagine a distributed network, okay, having different sites S1, site 1, site 2, up to n number of sites are there. Okay, and this collectively we can represent as a request set Ri. Okay, having a set one set of sites, just assume. So and this each site going to maintain a queue called as a request queue. So request queue is the data structure. It's like an array going to store details of the messages transmitted and received. Those kinds will be stored in the request queue. So the request queue contains mutual exclusion request ordered by timestamps. Based on the timestamp value only, all the request message will be ordered in the request queue. One more thing, every site going to maintain this request queue individually. Okay, so thereby we can know that who is on the top, who is going to enter into this critical section. It is fully based on this queue only. So the request queue is the major part of this Lamport's algorithm. Okay, so the algorithm requires the messages that will be delivered. All the messages stored in this request queue that will be delivered in the first in first out manner. Now we'll see with an example. Okay, so before seeing the example, you should know there are three type of messages only passed in this system, that is a distributed system. There is one is a request message, second one is a reply message, and third one is the release message. Okay, so these are three messages. What is the meaning of the request message? There is request means that is when any a site going to send are going to wants to enter into critical section. Okay, if a site wants to if a site or a process wants to enter into critical section, it was to send a request message to all the other sites. Okay, for example, if P1 wants to enter critical section, means the P1 will send the request message to all the other sites or the other process. Okay, and once it is once it is received by all the other process, so other process will send one reply message. Okay, that is called the reply. So once the requesting process received this reply message from all the other sites or all the other process only, it starts entering into critical section. Okay, and go to the critical section. It avails the resource. Okay, after that later, okay, after some time, it relieves from the critical section. Once it is relieved from this critical section, it the requesting or once one process already stayed in the critical section, right? So whenever it was released, it automatically sends the release message to all the other process. So it means that the process informs the other process that I have completed my task. Others can go and utilize the critical section resource. That is the meaning. That is the meaning of release message. Okay. So request, reply, and release are the three major messages are communicated in Lamport's mutual exclusion algorithm. Okay, now we can see an example. This is a simple illustration, okay, for a better understanding. So just imagine there are three processes, okay, process P1, process P2, and process P3. So in this three process, okay, now we can see how this critical section happens in these three process communication. We will see one by one. Just imagine first the process P3 wants to enter into critical section, okay. Just imagine process P3 is going to enter into critical section. That is the situation. Okay. So what's the first step? I told that first, what is first step? The P3 has to send the request message to all the other process. Okay. Are you all clear? Students, are you listening? Yes, ma'am. Okay, okay, okay. So now the process P3 send the message, request a message to the process P2 and process P1. Okay, this is the request message. This is the first message. Now it is sending. So when it sends this request message, the request message itself has two field. I told that each message includes timestamp and process ID. So the process P3 maintains the request queue. This is the queue Q3. Okay, because Q3 means what? The Q3 is the queue maintained at the process P3, and it has two field. One is timestamp, another one is process ID. This is third process, so process ID is 3. Okay, and timestamp is timestamp is generated by the clock itself, by the system clock itself automatically generated. Just assume here the timestamp value is 1. Since this is the third process, so the ID of the processor is 3. Okay, and this is the request queue Q3. When it sends the request messages, the same copy, that is TS1, okay, timestamp 1 and process ID 3 will be shared to all the other processes when it sends the request message. So at the time the process P2, we have the queue called as Q2. There also we have the same copy TS timestamp 1 and PID 3. Similarly, at the process P1, it maintains its own queue, request queue. Here the queue is named as Q1. This is for the P1, so Q1, and it also has the copy of that is same detail timestamp. Site information is also shared to the remaining processes P2 and P1. Why it is sending request message? Because now the P3 wants to enter into critical section. So before entering critical section, it is sending the request message, getting permission from all the other processes by passing this timestamp and its process ID. Okay, I hope it is clear. So now once it is over, what is the next step? All the other processes going to respond, right? So before responding, what happens here? Now the process P1 wants to enter into critical section. Now the problem happens. Actually, what is the step? I told that when it after sending the request messages, immediately what all this accepting messages are going to reply with the P3 that we are accepting. You can go and proceed to go with the critical section, right? So before getting this reply messages, what happened? Now the process P1 starts sending the request messages to all the two. What is the meaning? So now Pi wants to enter into critical section. Okay. So what about this P1 now? P1 in the queue, there is queue. This queue is updated now. Q1 is value is now its timestamp value is 2. Okay, and its process ID is 1 because this is the first process. And here for the Q2, here what happens is actually whenever any new processes, whenever any new request messages are coming, the all the there is the queue stores all the request messages that will be stored in a timestamp based value. Okay, it will be in a order. Here already we received this timestamp 1, right? So timestamp 1 is the less value. Always the lesser value will be on the top of the queue and the highest value will be on the bottom of the queue. Like that all the values will be stacked, all the values will be pushed into this queue. Okay, wait a minute. Okay. So now what happens? P1 wants to enter into critical section. So for that, P1 is now sending the messages. Okay, request message to all the remaining process P2 and P3. So now what happened? Q1 is the process P1's Q is called as Q1. Its timestamp value is generated as 2 as the value and its PID is 1. Okay. So based on this first in first out fashion, all these values will be timestamp values will be updated on the all the queues at the P2 and the queue at the P3. Okay. So at the same time, the Q1 also now updated. Okay. TS1 PID 3 because the lesser value in this one more case, this Lamport algorithm considers that the timestamp with the lesser value will be treated at the highest priority value. Okay. That will be processed first and the highest timestamp value will be processed the next. Okay, always the lowest timestamp value will be processed quickly or at first. Okay, so in this way all the remaining no remaining process also received by this request messages. Okay, so now what's the next step? Now the P2 is because P2 is not going to enter into critical section. It is not having any interest, right? So P2 quickly sends the response to this P3 process. You can enter into critical section like that. It is giving a reply message. Okay. At the same time, P1 also sending that. P1 also sending the reply that you can enter into critical section. Okay. One more case. In the case of P1 also send the request, right? For that P1's request, what is the response now? P3 giving the permission to P1 that you can enter into critical section. Okay. P2 also giving the answer response because P2 is not going to make any trouble. P is not interested to enter into critical section. So P2 also directly given the permission as a reply message. So now P1 also got reply, P3 also got reply, right? So now both are having the equal probability of entering into critical section. But at a time we can allow only one process in a critical section. Now here is the problem. So what to do is here we have to use two rules. Okay, these two rules only very important Lamport's algorithm. Based on these two rules only, at a time only one process can be allowed inside the critical section to use the resource. Okay, what's the first requirement? Process timestamp. What is the TS here? TS denote timestamp. The timestamp is always on the top of the queue. So in each request queues, we have to check all the request queues. The request queues having various timestamp values, right? We have to focusing on the timestamp value available on the top of the queue will be given the most important priority. Okay, should be on top of the queue. And the second thing is what? Second requirement is process should receive a reply message from all the other process. Here in this case, P1 also received the reply messages, P3 also received the reply messages, right? Now both are having the equal probability. What is the only difference here? We can go with that this timestamp on top of the queue. Now we can check that timestamp value on top of this queue. There is Q1, the top of the queue value is what? TS1. It is PID 3. There is process 3 only given on the top. Here also 3 on the top. Here also 3 on the top. So what is the meaning? Now all three processes come together concludes that PID process 3 is going to enter into the critical section first. Are you all clear? Okay. So once this process P3 enters into critical section, okay, it goes into the section, it takes the resource, and once the process successfully done, what is the response? It has to provide the release message, right? So when it releases this from this critical section, it sends the release message to P1. At the same time, it sends a release message to P2. Okay, so whenever it is sending, what happens? Its value has to be updated. Okay, there is Q1 value is now, there is now T1 work, there is a PID3 is now over, task completed, so it is removed from the queue. Here also the PID3 details timestamp will be removed from the Q2. Similarly, Q3 also removes the PID information. Okay. So now which is available in this queue? Only TS2, that is timestamp value is 2, for the process ID 1 is available in every queue. Okay. So now we have to again check the condition. There is next we are going to allocate what? P1 is ready. We know that P1 is ready, but as per the algorithm, we got to check these two conditions again. Okay. Process timestamp T is on top of the queue, is now top of the queue is only what? PID1 with timestamp is there in top of the queue on all three queues. And second condition is process should receive a reply message from all the other process. Yes, already P1 received the reply messages from all the other process. So now it's time for the P1 to enter into critical section. I hope everyone is clear. So now P1 enters into critical section easily. Okay. So after its task, after it's using the resources in the critical section, it again replies with a release message. Okay. It has to be released by the critical section. So it sends a release message to P2 and also release message to P3. It is informing that now the critical section is free for others use. That is the meaning. Okay. So this way the communication is happened. There is now you could see that how the communication is done. What are three messages passed here? Request, reply, and release. So when the request is used before, that is before starting communication or before entering into critical section, when a process wants to enter into critical section, first it has to get the permission from all the other process by sending a request message. Okay. Then the process has to get the reply message from all the other processes. After receiving the reply messages, then the particular process can enter into critical section. Okay. After the task is completed inside the critical section, it sends the release message to all the other process. That's all. So when the problem happens, when there are two or more processes going to enter into critical section at the same time, then we apply. We have to think about this. What? These two criteria we have to follow. Okay, the process timestamp is always on top of the queue, and every process must receive the reply message from all the other process. Okay, so once it is satisfied, then that particular process only eligible to enter into critical section. After it is released messages, then the remaining process based on the again these two conditions, another process can enter into critical section. Okay, I hope you all understood. So now we can enter into algorithm. Lamport, this is the Lamport's mutual exclusion algorithm. There are three major steps: requesting the critical section, executing the critical section, and releasing the critical section. Okay. So the first step, requesting the critical section. What happens? So what happens here? The first step, requesting the critical section. Suppose if a site or a process wants to enter into critical section CS, it has sent the request message, right? Request message along with its timestamp and its process ID or the site ID, okay, to the all the other sites in the network. Then it places this timestamp value in the request queue also of a particular site, okay. And when the particular site receives the request message from the all the other site from the opposite site, okay, then it returns the reply message, and also it has to update its own request queue also. Okay, so then the second step, executing the critical section. So here there are two conditions. I told that one is what? Timestamp will be larger than the one, that is always on top of that. Always they will the queue will be arranged in a that is a larger will be of on the lower value and the less value will be on the top. And one more condition is there, that is the values on the top will be processed first. Okay, the top value will be that considered as a highest priority value here, the Ramport's algorithm. It will be processed first, that can enter into critical section. Okay, and the third step is releasing the critical section. So here releasing, in this situation, once it is exiting from the critical section, the process sends the release message to all the other process. Okay, so at that time, on the top of this queue also updated, right? It should be removed from the top of the queue. Okay, and it sends a release message to all the other sites in the network. Okay, so that's all about this algorithm. There are three major blocks or three major steps involved: request, execution, and release. So now finally we can see the performance of this algorithm. So the performance is given as, that is 3 times n minus 1 messages are passed or communicated per critical section invocation. How 3 times n minus 1? Here n means, for example, here we have taken 3 processors, right? P1, P2, P3, we have taken 3 processes, so n value is 3. So what is n minus 1? 2 minus 1. So there out of 3 processes, only one process going to send the request message, right? So the remaining 2, that's what n minus 1. So how many messages are there? So n minus 1 request message will be transmitted, n minus 1 reply messages are communicated, similarly n minus 1 release messages are communicated. For our case, n value is 3, right? 3 process. So we have to check now, there are 2 request messages. N minus 1 means what? 2 request messages, 2 reply, and 2 release. Now we can check this here. See here, there are 3 processes, right? For example, suppose P3 wants to enter into critical section. How many request messages are sent? 1, 2. There are 2 request messages. How many reply P3 receives? 1, 2. There are 2 reply. How many releases? After exiting this critical section, P3 releases 2 releases. 1, 2. Got it? So there are 2 request messages, 2 reply messages, and 2 release messages for a particular critical section. For a single critical section entry exit process, invocation process needs 3 request messages, sorry, 2 request messages, 2 reply messages, and 2 release messages. Okay, so that's what it is given, that 3 times n minus 1 messages are communicated per critical section invocation process. So that's all